Jahnavi madam, am I audible? Hello. Please let me know. Am I audible, madam?
Yes, sir, you are audible, sir.
Yeah, okay, thank you. Okay, thank you.
Yeah, Kondareddy, sir. Hello.
Yes, ma'am.
Sir, with your permission, we will read your profile, sir.
Yeah, ma'am. Please go ahead. Yeah.
Yes,
No.
sir. Now I invite the Professor, Mr. Tippaswamy, sir, to introduce.
Yeah, okay, sure, madam. So, hello all. Good morning to everyone. So, I welcome to all participants and researchers to All Indian Council Technical Education sponsored 1 week online short-term training program on machine learning, recent trends and applications, phase 4. So that is from 21st June 2021 to 26th June 2021. So I am C. Tippaswamy, Assistant Professor, so Department of Electronics and Communication, Srinivasa Ramanujan Institute of Technology, Anantapur. So it gives me a great pleasure to introduce today's session resource person, Dr. Kondareddy Mopuri sir, who will be the resource person for day 2 session, that is 11:30 a.m. to 1 p.m. That is on 22 tree-based methods for machine learning. Sir is currently a visiting faculty member at the Department of Computer Science Engineering, Indian Institute of Technology, Tirupati, so where he works on especially deep learning and computer vision. And Sir did a PhD in 2018 at the School of Informatics, University of Edinburgh, UK. Sorry, it is the experience. Okay, and he has a senior software engineer at Samsung R&D Bangalore, India, at the duration of 2011 to 12. And Sir education Institute of Science Bangalore, and he's a post graduation in the discipline of visual information info processing and embedded systems under the Department of Electrical and Electronics Communications, IIT Kharagpur in 2011. And his graduation is completed in the Department of Electronics and of Engineering, JNTU Kakinada, at 2011. Sorry, in 2009. And Sir has many awards and academic achievements. Okay, and is awarded a doctoral dissertation award recognition of his PhD work in the area of pattern recognition and artificial intelligence in 2018. He has best awarded as a doctoral dissertation award. So that is the recognition of his PhD work by the SPOCOM conference in 2018, and he's awarded as a best paper award in technical session. So that is the best student paper in the SPCOM conference, that is in 2018 also. And he received grants worth of $1 lakh. So that is awarded for his research during, and Sir has an highest gate percentile, that is secured 99.57 percentile. So it is a very great achievement, sir. We're fortunate to have you here. And that is in 2009. And also he has gotten a AIEEE best rank, that is the All India rank of 1048. So that is among 4 lakh candidates appeared for that exam. And in MSET also, Sir has an AP MSET rank of 189 among 1,15,000 students appeared in 2005. And Sir has a teaching experience, that is in Artificial Intelligence Department of CSC IIT Tirupati, and that is from January to May 2021. Okay, and SAR has a very vast research interest area. So that is learning over long-tailed training data and data engineering for deep learning and robustness in deep learning against adversarial perturbations and adaptability and interoperability of deep learning models. And SAR has one book chapter. So that is a deep learning for medical image analysis. So that is published by Elsewhere, January 13. Okay, and SAR has a forum of peer-reviewed journals publications, and he has peer-reviewed conference publications of number 15 number. Okay, information of our resource person, Dr. Kondareddy Opere, sir. So I once again welcome to this session, sir.
Thank you,
So
sir.
my dear my participants, so be ready for this session and all the best. So I thank to everyone for this given opportunity.
Thank you, sir.
Thank you, sir. Thank you very much, sir.
Yes, yes. Thanks for the very warm welcome.
Yeah, thank you, Tipayaswamy sir. Kondareddy sir, the session is over to you, sir. You can present your screen.
Okay. All right. So for bandwidth reasons, I will stop my video. And yeah, this I would like to have it an interactive session. That means, whenever you have questions, feel free to stop me at any point during the presentation and ask your questions. Yeah, if there is any hand raising or speaking over mic, that is fine, or else you can post the questions in the chat box. I'll be looking at them. Yeah, but anyway, in the end also you will get some time for interaction if there are any questions, so no worries. All right, yeah. So thanks for a warm welcome and thanks for inviting me to this STTP. Hopefully I'll discuss some of the useful concepts and you'll be equipped with some of the machine learning tools. All right, particularly today we will discuss about tree-based learning methods. Yeah, so these are very important, and some of the people may think relatively, classical machine learning tools. But let's see, we'll find out what they are and how we can use them, what are their advantages, disadvantages, when to use them, all that. All right, so today's agenda is we'll use tree-based methods for both classification and regression problem. So as we all know, predominantly the machine learning tools are classified into either regression or classification tools. So what do we mean by regression? Regression means, we are predicting a continuous variable here, a quantitative variable. For example, predicting the temperature, which is a real quantity, 32.5, 23, 17.8, minus 1.2, all these values are possible, right? The predicted variable y, which is the output of the model, is a continuous value. On the other hand, classification is basically, there will be a set of outputs. For example, if you are predicting the eye color of the people, there are only 3 or 4 values they can take: black, brown, blue, some cases green, if possible. Yeah. So these are, there is no continuous value that is we are predicting. Instead, they are labels. They are discrete values, a set of predefined values from which we are assigning to the input, right? The input will be assigned one of these values. So there is nothing in between black and brown eye color, right? Either it is black or brown or blue, or if there are any other labels we have, that, right? That is qualitative variable, right? That is the difference. Regression means you're predicting a continuous variable. Classification means you're predicting a label, which is one of the values, one of the possible values from a given set. So the trees can be used for both the problems. We can use them for regression, and we can also train the model to classify the input based on the input features. All right. So I'll try to summarize the tree-based methods and then go in detail. So what do we mean by, yeah, so how tree-based methods operate is basically they involve segmenting the input space. Segmenting means, making the portions, separating the input region into specific regions. Each of the regions will assign a different value from the others. So in the input space, you are making regions. You are segmenting the input. So input space or predictor space, both are same. Predictor means X, which is the input to the model. Output is Y, which is the, there seems to be a question. So can we use it for nonlinear data? Yes, we can use that. But there are some limitations. We will see. Yeah, we can use them. Correct. Right. Yeah, so as I was saying, tree-based methods, what they basically do is, how do they process the data? How do they predict the output is basically the input space is segmented into multiple regions. Each of the region will have the particular output, right? So because there are some rules involved in segmenting the input space, sometimes they are called decision trees, because the decision of what output is to be assigned is based on some rules. The same rules are used for dividing the input space, right? For example, I think we will take an example and go ahead, but the basic fundamental concept in tree-based methods is segmenting the input region based on the features and then assigning different values to different regions. There are some rules which decide how to segment, how to divide the input region. They are called decision trees also. All right. Yeah. So some important aspects why generally tree-based methods are preferred. Why the researchers and engineers would like to process the data using tree appealing factors. So they're simple and they're very useful to interpret. Interpret meaning to understand what is happening, to explain why the method has given a particular output. So that is very important, particularly in applications where understanding the model is very important. For example, in medical diagnosis, right? An expert uses an AI algorithm to diagnose whether the patient is to be operated immediately or not. These things will predict yes or no, but that is not good enough. It has to say and explain why it is predicting whether he will be paid. So this is a simple regression tree, which is learned for predicting the baseball player's salary. Again, the inputs are important features, which are the experience of the player and the recent form of the player. Right. This is how a typical regression tree looks like. Okay. Now let's go into how to achieve this kind of a decision tree. Right. So as I was explaining, so how to read a decision tree is like this. So start from the top, and the input features are clearly given based on which the decision is being made. At this point, what input feature is used? His experience, his or her experience is being used to separate the path. This is the top split, and after that there is another split here, which is on the right side of the top split, which is based on the second feature, the form, recent form, right? All right, so this is R1, the region 1. As I said, if you remember, we said that the fundamental idea of decision trees is to segment the input space. The first segment is this one, R1, where all the players whose experience is less than 4.5 will fall. All those players, relatively new players, will fall in this region. And this region, experienced players slightly out of form, this region, R2. And the third, for the rightmost region, is experienced players who are in good form. So this is how you segment the input space based on the features, right? So more mathematically, it looks like this. R1 is the set of input X such that the experience in years is less than 4.5. Similarly, if you describe mathematically the second region and third region, this is how they look like. All set of all X's such that the experience is greater than or equal to 4.5 and the recent hits they have made is less than 1.117.5. Similarly, R3 is same set of all X's such that the experience is greater than or equal to 4.5 and the number of hits made in the last year is greater than or equal to 117.5. Right. Of course, this is very simple. It is easy to see and easy to understand. But think of a big or a complex tree also. As long as you have these input features and the thresholds based on which you are taking different paths, it is easy to read, right? Without such descriptions, right? Even if I don't have these R1, R2, R3, I can clearly see and understand what is happening. Okay, if the player is not experienced, they are paying this much. If the player is experienced and he has good, relatively not so great form, that is what they are paying. And if everything is fine, the player is experienced and he's scoring good in the recent years, this is what he's getting paid, right? Such a simple, effective way to convey the decisions made by the algorithm, right? But yet we haven't discussed how we achieve these threshold values. We will see that. That is the crux of the algorithm. That is the very important. That is where we look at the training data and decide. We'll come to that. Before that, let us describe all the different aspects. All right, so these leaf nodes. So think of it as a tree. These are branches, and where there is no more bifurcation, they are called leaves or terminal nodes. These are internal nodes where things are getting divided here and here. These are internal nodes. But if you see this, and this, these are the end points. They are terminal nodes. I mean, tree is getting terminated there, right? So these are very important. This is where the regions are formed, R1, R2, R3. So that some terminology is these are internal nodes. All right, so this is how it looks. I was telling about segmenting the input space or stratifying, partitioning. These are all same words, meaning x-axis is experience in years, y-axis is the number of hits made in the last year league matches. So recollect the topmost split, which is based on the years feature. If it is less than 4.5, all those input forms region 1, R1. So the yellow colored dots are the training data. These are all the players data. They have taken a lot of players and their statistics, how many hits they have made in the recent year, how many years they have been playing, all that. So if you see that, this is all R1, and R2 is players with more than 4.5 years of experience and who have scored less than 117.5. So y-axis is increasing towards the top. So that is why all the region below 117.5, this forms R2. And this is R3, which is greater than 4.5 years of experience and who scored more than 117.5. So all these regions will be paid 5.11. This players will be paid 6, and this players will be paid 6.74. That means E raised to $6.74,000 will be paid. Right. So this is how the partitioning happens based on the input features. There is no data point which is not covered, right? Every point will fall in at least one of, at most one of these regions, either R1, R2, or R3. There is no ambiguity. Only one of these regions will cover every point. So there is no ambiguity, and they are non-overlapping also, right? So everyone is clear how much they are getting paid. All right. So again, I was telling you, right? Although the predictive accuracy may not be the best, the trees are very good and very, very useful in interpreting data, right? So let us try to interpret this particular decision tree. So how do one as a user or as a developer, look at it and interpret the decisions made by. So what do we infer? It is clear that experience is the most important factor that determines the salary. Why? Because the first split is based on the experience. So this is how we should understand. After solving this problem, as a machine learning engineer or developer, we should understand the process. Right? This is a very simple example. We clearly know without even applying machine learning tool, we may be able to know experienced players will be paid more. And also, think of a very complex problem. A lot of factors are being involved. There, it may not be very trivial. It may not be very easy to see. But the trees can bring that up because based on that factor, the years of experience, that is where the first split is happening, right? So that is what one can read easily. Experience is the most important factor that determines the salary. Also, players with less experience earn less because the output variable, which is 5 point, how much is that exactly? 1, 1. Yeah. So that is also another inference we get to know. Less experienced people will be paid less. At the same time, given that a player is less experienced, the number of hits he made is in the last year may not play a good role because it, all the players with less than 4.5, it doesn't matter how many they scored. Somebody is scoring close to 200, somebody is scoring very less, like 10, 20, 30. Equally paid. So that is something which is, yeah, that may not be a correct thing to do, but it is visible from this graph. So that is also second inference. And the third and important inference is, for the experienced players, number of hits made in the recent league affect their salary. That means more hits will bring them more money. So these are without even specifically whoever designed this need not tell everything in this clear detail. The graph itself is very, very clear, very easy to interpret, understand, right? So that is the beauty of decision trees. So now think of a very complex problem with more than 10 input features. The features here is only two number, right? Years and hits. But complex problems will have more features. Let's say 13 features are there. So then it may be difficult for us to easily decide. That is where we should go for trees and other tools. All right. So this is the beauty. Interpreting the tree is very, very easy. And then let us also see the other side. Maybe the decision tree is making the things overly simplified. That means the relation between experience and the recent form may be more complex. For example, as I said, if the players are less experienced, it doesn't matter how many hits they are making. They're all getting the same salary. That may not be correct, right? They should also have a different salary based on their recent form, right? So that is overly simplifying. Because of that, we are losing. The some of the players are not happy, right? So this is a side effect. Oversimplification may happen at times because of the trees. However, the advantage is that easier to interpret again. Nice graphical representation is there. That is why some cases they fit to be used. All right. So now everything is fine. We understood what is happening when even a non-expert, if he or she sees the decision tree, it is very easy. Okay, how the model is predicting. The model is looking at, if the player is experienced, it is looking at his recent form. If the form is good, it is paying more. If the form is not so good, it is paying less. Things like that, right? So everything is fine. That is fine. Now let us actually go into how the model is being built, how the tree is being built, how the thresholds on those years and the hits is made. Let us see. So we have to divide the predictor space. So the input space, for example, we are in a p-dimensional space. That means, so in the previous example, it is only two. X1 is years, X2 is hits, right? There are only two input features for the model, but in general, there will be more. Let us say there are p such things. right? For example, if you're doing a medical diagnosis, your BP, sugar, and other blood test reports, and a lot of other tests they make, and everything will become the features. So there can be p such features, and then based on these input features, we have to divide the input space into j distinct and non-overlapping regions. So this is the goal, to build a regression tree. But how do we decide how to split? So yeah, so before that, let me just take you what will be the prediction value for every rj. For example, let's go to graph. Yeah, let us say this is what the split is after building the tree. This is what the segregation looks like. So what value should I assign to all these players? What value I should assign to all these players that are falling into R2? So one easiest way is look at all these training examples that are falling in this region and take the mean salary, right? Average of all these players' salary. You take that and assign. So during the testing period, you try to see where the test sample falls. Let us say it is falling in R3. So what you do is, in the training data, you will have a lot of players that fall in R3. You average the salary of all those players and assign that value to the test. Similarly, if the test sample falls in R1, so what we do, we have the training data which falls in R1. Let us say 70 players are falling in R1. So take the mean salary of all those 70 and assign to the test sample. So that is how the model assigns the value. And you can clearly see the same value will be assigned to every point in the particular region. Although it is a very gross approximation, that is what is happening. So I want you to see that, right? For all the test cases that fall in one region, the predicted value is same, right? That is also some applications, I mean, it all depends on the application. Some applications, it may not be fair. It may not be correct thing to do also. But think of very small regions. If the region is very small, then it may be okay, right? Think of very, very small region like this. If the region is very small, all the people within that region may get the same salary. That is okay, because their experience is same, their recent form is also same, then it is okay. But the error becomes more if you have bigger and bigger regions. For example, see here, this particular player is close to 1 hit, and this particular player is close to 200 hits. So both of them get the same value, same salary. Sometimes like this, it may look unfair, but of course, it all depends on the application and how small your regions are, all that, right? Yeah, you have to be aware of all these things. When we are designing or using this algorithm, we need to be aware of all these things. So that is how a prediction value will be assigned. Mean value of the training samples that are falling in that region. All right. So let me just go back. Right, this is where we are. So after dividing, what we will do is we will keep the mean value, so that if a test sample falls in that region, we will take the mean value of the training value and assign to the test value. Right. Now, how to construct the regions? So they can be of any shape. So in the example we have seen, it is very simple. It is looking like rectangles. But theoretically, there is no, you can have any arbitrary shape also. But then if you want to have a different shape, more realistic shape, it will be more complicated. The simplest thing to do is we can think of high dimensional rectangles, right? Rectangles are easy because, based on a feature less than equal to something and greater than equal to something. So if you have a simple threshold like that, the regions formed will be looking like a rectangle. So that is why almost all the people use rectangle shapes, but there is no restriction. Theoretically, you can use anything because of the simplicity. Why it is simple? Because these shapes can be realized easily. X less than or equal to one value, X greater than that value will form a rectangle automatically, right? If you see, again, let me go back to the image. So X, the Y years, experience less than or equal to 4.5 and greater than 4.5. So simple in this box, right? So that is why the shapes are more practically high dimensional boxes. All right. So the goal, what is the goal here in dividing? The goal is to minimize the residual sum of squares. So what it means is basically, so there are j number of rectangles, and within each of them, the actual value minus the mean value, we are minimizing. So you remember I was mentioning, if the region is very big, there will be difference. There will be a big difference between the salary paid to one and the other candidate, right? So that we have to minimize. So the mean response of the training observations that fall in the jth box is represented by y hat of rj, right? Rj is the region, jth region. You are taking the mean salary or mean response of all those training samples, and your box should be like that, which minimizes the difference between the mean and the actual. Think of a very small or very tight box where there is no spread. Most of them are falling very close. In that case, the mean value will be very close to the actual values, right? Everybody is earning the same value or very close values. In that case, the mean will be very close to this and the residual sum will be less. So the goal is to find such boxes. We need to find such boxes where the mean value will be closer to the actual values. So this is the training procedure, how to divide, how to get these regions R1 to RJ. So yeah, you may stop me if it is not very clear, but yeah, I'm proceeding slowly. Right. Different, I mean, infinite possibilities for dividing the input space, right? So even for a small problem of this salaries, because X is a continuous variable, right? Number of years or the how much is the experience? It can be, 2 month, 2 year, 1 month, 2 year, 2 months, anything. It is a running variable, continuous variable. If you want to actually find out by varying continuously, it is computationally very, very expensive. In almost infinite number of um, cases arise, right? How to divide. Because of that, what we do is we do take a greedy approach. If you want to investigate all such possibilities, it will not converge. It will take ages. So what we'll do is we'll take a simple top-down and greedy approach, which is called recursive binary splitting. So we will see what it is, recursive binary splitting. So top down, because we start from the top of the tree and then go on recursively splitting. So you'll start with two regions, R1 and R2, and you pick one of these R1 and R2 and again recursively split into two. So that is why it is top down approach, because we are starting from top and going down and recursively splitting each region. Greedy approach, whenever you see greedy approach, so this is what we should understand. We are not looking for the best, like the best possible. We are not looking, because it is very expensive computationally. So what we do is we can take a greedy approach, which is at this point in time, what is best to do. I don't look into the future. I don't look into the other aspects completely. I'll simply look at, given at this point in time, what is the best action to take. So not only in the decision trees, you see in machine learning and data science, a lot of algorithms use this greedy approach. So whenever it comes, you should understand that, okay, we are not looking for the best, because it may, what we are doing is, given this situation, what is the best I can do? That is what I am going to do. I don't investigate, okay, if I take this action now, what will be the next thing? Will it be also best? No, I don't go recursively. I'll just do at this moment what is the best thing to do. So a lot of practical machine learning and optimization happens based on the greedy approach, right? So I'll show you how exactly we'll do. But what exactly we're doing is, at each step, best split is made at that particular step, rather than looking ahead and picking a split that will lead to a better tree later. So overall, whatever I'm doing may not result in the best overall performance, but at this stage, is it best or not? So that is what the step only I'm worried about. Not looking into the future, is it going to result in a better tree or not? That I'm not worried. Okay, so even more specifically, how to proceed? I'll start with the feature. All features I look into. So in this case, there are only two features: experience and hits. And then what is the possible value? Cut point means, what value. For example, 4.5 is the cut point for the first split, right? The years of experience less than 4.5 and greater than 4.5. That is one cut point. So you can think of, you can start from 1, 1.5, 2, 2.5, 3, 3.5, all the way. What is the maximum experience? You can go all the way, right? You have to consider all these values and split. And once you split, you have to compute the RSS, residual square sum of squares. So if I split based on 1, experience less than 1 and greater than 1, what will be the region formed? I compute, y minus y mean whole squared for both the regions, the value aside. Now I'll make 1.5 my threshold, and now compute R1 and R2 and compute the RSS for R1 and R2. I'll keep the sum again. So if I go on changing, yes, my R1 and R2 change, right? So out of all those values, what is the minimum? I'll pick that one. So that is the greedy approach. So I'm not, going another round. Okay, now I'll pick R1 and R2. I will see one more round. If at all the resulting R2 and R3 are also minimum, then only I'll pick. So this will not end, right? So that is what is called, absolute maxima or absolute minima. That we cannot do here. Instead, we are doing greedy approach, right? So let me just, take to the board 1 second. That way, things will be more clearer, I think. Are you able to see the white screen? Somebody can respond. Okay, great, thank you. So this is my x1, this is my x2. I can divide, right? I can divide here, I can divide here, I can divide here, etc., etc. So what I do is, what is greedy approach is, so based on the yes value, let us say it is 1, I'll form R1 and R2. There will be a lot of training data, right? Whatever yellow dots I have shown, you can think of them. And I'll compute the RSS based on this. There can be different training points. Based on this threshold, I'll compute R1, and this becomes R1 and this becomes R2. RSS will be J is equal to 1 to 2, Y, again, there can be different values, YK minus Y hat K, right? Whole square. Yeah, so this is RSS, and I'll keep this value. Let's say this is 10. And now I'll go for another threshold. So I'll vary the threshold, which can be this time 2, right? Years of experience is 2. Now my regions will change. This becomes my R1 and this becomes my R2. So there may be some points earlier in R2, now go to R1, right? So based on this was S is equal to 1 and now S is equal to 2, the cut point. I'll compute RSS again, I'll keep it 20. Again, I'll move towards the right. S is equal to 3, 22.3, something like that. S is equal to 4. Let us say this is only 5. S is equal to 5, and so on. I'll compute, 101.2, something like that. Wherever the minimum occurs, I'll pick that value for the first split. So this is called a greedy approach. So I'll change the value of S for X1. So I have to do this for other thing also, X2 also, because there are two features, right? I have to do this, and splitting in the vertical space also I have to do. So I'll do this, and whatever is the minimum RSS, I'll pick those cut points. So that is how I decide. Minimizing the RSS is the criterion. Why? Because it looks like a more appropriate prediction value, because this is what we are predicting for all these training samples, right? That is why. So whatever gives in the minimum error, that is what we should pick. All right, I hope this is clear. Yeah, again, I'm sorry. Yeah, so first we select the predictor xj and then the cut point yes. So what value leads to a greatest reduction in RSS? So that value we will pick. So mathematically, all this boils down to like this. I'll investigate which xj, whether it is x1 or x2. And once we pick x1 or x2, what is the value? Whether it is 4, 5, 4.5, all these values we have to investigate and seek the value of j and s. That means, you know, you have to keep all those errors and then pick the value that minimizes this sum of residual sum of squares. Right, this is how we construct the region Rj. And now once we split into R1 and R2, we have to repeat the same process. Look for the best predictor and best cut point that minimizes RSS further. Right, once you have two splits, now go to the left split and try to split again, or go to the right and split again. How to split? Based on you go on changing the value again and form R2 and R3 and compute these errors again. If the sum is minimum or lesser than what we have already, then go for the split, right? But this time we split on one of the two previously identified regions. We don't go back. Once two regions are split, we will pick one of them and do this. So it goes on recursively, one after another, one stage after another stage, we go on doing this, right? Of course, it looks a little complicated because we are investigating for that particular that particular cut point where we are splitting. So that is what we do. So we continue until a stopping criterion is reached, right? What is the stopping criteria? Let us say until all the regions will have at least 5 points, 5 players, right? We cannot have splitting with less than 5 players. So that is one of the criterion, right? This is not a bad criterion because yeah, we cannot, you know, go on splitting until one region will have only 1 point. That is useless. It is kind of remembering all these salaries, and then only, you know, if the test sample matches, you assign that prediction, that salary, right? So again, this is all application dependent also. So how to come up with the stopping criterion, all this thing is not very clearly defined. I mean, understandably, because these things vary from problem to problem, application to application. So as machine learning engineers and scientists, what we should understand is there has to be a stopping criterion which makes sense in that problem, right? So this is how we stop. Once the regions are identified, as I said, during the testing, the prediction is the mean response of the training samples in that region. We compute the mean salary of those players that are falling in a particular region, R1 or R2, R3. And whenever the test sample falls in, let us say R3, whatever is the mean salary of those training samples, we will assign. Yeah. So this is how it may look. This is one of the possibility with 5 regions. So R1 is when X1 less than T1 and X2 less than T2, right? So this is how you can clearly see based on X1, the first split is happening. Everything less is on another one split and everything greater is on another split. And again, you go to R2 and find out whether to split based on T1 or T2. Seems like based on T2 is better. As I was saying, right, a player here should not be given the same salary. That means, you know, player who's scoring more and who's scoring less will get the same salary. That is bad. So that is why we'll have another split where the recent score is less than T2 or greater than T2. If it is greater, you will assign some salary. If it is lesser, you will assign other salary. So this is a good division. And on the R2 side, which is this, we have X1 less than or equal to T3 and greater than. So again, after T1, there is another experience. Let's say experience less than 6 and greater than 6, things like that. If it is less than 6, you know, same salary is assigned. If it is greater than 6, again, if the players are performing better than the rest of them, you assign more salary. So this is how, you know, this is an example. I wanted to give you how it looks like. So in total, you have 5 regions in the end, right? This is one of the possibilities. All right. So what is the problem here? Because if you go on doing this to incorporate only a limited set or very close set, there may be the possibility for overfitting. So above procedure may give good predictions on the training data because the training data is what is used for minimizing the residual also. No, that is why yi minus the mean, right? So the mean is computed from the training data itself. That is why it may happen like that. Why? Because I think overfitting is understood by most of you, but let me just tell you what it means. So overfitting means if you bother too much about the training data and try to minimize the error on the training data, it kind of fit closely to the training data, which is bad because any deviation from the training data will suffer a lot. And it is most likely also training data and test data come from the same distribution, but again, we should not be completely remembering the training data. We should take it as a guidance, but it should not be like completely remembered. It's like mugging up, right? That's not good. We should understand the concept behind the process. So that is what overfitting means in this case. Yeah. So how to avoid that? Because if you so this is bias variance trade-off is also there. So what exactly is happening here is when I say it is giving too much importance to the training data by reducing the RSS as much as possible, what it means is uh, okay, let me so okay, let me very briefly tell what is happening. So the model is becoming more sophisticated, and because the training error is minimized, right? In the training error sense, it is more sophisticated. That is where the uh, uh, variance with different model, different data. For example, okay, let me find a suitable way to explain this. Yeah, so what will happen if you error? The tree looks very complex, very complicated, because everywhere there is a cluster, you will try to have a block around it, right? You essentially create more blocks, more regions than required. So that is when a training data, testing data will suffer because of the more and more segmentation. Testing data may fall in an inappropriate bin, getting an incorrect salary or incorrect response assigned. So that is what happens. That is called overfitting, right? So generally, smaller tree with fewer splits is preferred because smaller tree will avoid this kind of overfitting. So with smaller tree, because the number of bifurcations, the number of regions is also small, that way it is not completely dependent. It's not closely dependent on the training data. So you have to remember as a designer that training error reduction is important, but it is not the only thing we should focus. We should make the model also simple. When you have the simple tree, smaller tree, the error may be slightly high, but it will generalize better. The test error would be better for this case. So always keep that model simple, right? All right. Yeah, how to achieve a smaller tree? Uh, we go on bifurcating because the RSS is reducing. We go on, splitting. So at what point we should stop? Yes, there is this criterion when the resulting regions are having at least some points, let us say 5 points or 10 points. There is that criterion, but with that criterion also, the overfitting may happen. That is why we need a sophisticated technique. So what is that? Build the tree only when there is a decrease in RSS by at least some value. For example, if the RSS is decreasing only by 1 or 2, you don't need to go for it. If the reduction is significant, if it is reducing by 25, 50, things like that. So I'm giving you some random numbers. Again, that value depends completely on the problem, right? What is the threshold that I'm telling? It is a application dependent. So we should not entertain every split. We should entertain only if the reduction in RSS is significant. Only then we should go for it. But it has also another problem, because it may reduce the error small by now, but once you do that, later stages may increase, may decrease the error more, right? So that is not being considered in this threshold. So that is why it is called short-sighted. It is not looking into the future. So if you accept this smaller reduction now, it may result in bigger reduction later. For example, let us go to the, here. So I'm reducing, imagine only this stage, only left side and right side is there. And then left side is another split happened based on T2. So R1 and R2 and R3 is there. Let us say that. So now I'm thinking whether to split using T3 or T4 or not, right? I'll compute the RSS. It is reducing only small. So if I don't do that, it will stop bifurcating again using T4 with R4 and R5, right? So this is called being long-sighted. If I accept this bifurcation using T3, I will be able to do later based on T4 here. If I do using T3, I'll be able to do later. If at all I stop, I don't want to do here, I will not be able to do this. So sometimes these thresholds may play that role. So you need to be a little careful. Yeah. So this may happen, right? All right. So all this is fine. I'll be using appropriate thresholds, and I'll be able to reduce the RSS by significantly. Even then, it will have lot of branches, lot of terminal nodes will be there, right? Again, so because we have taken a very simple example, you will not be able to see that. But think of a very complex problem, as I said, a medical diagnosis where you have more than 10 features. And I mean, more than 10 features is really difficult for us to remember what the features are, right? So think like that scale. If the problem is that complicated, you will have a lot of terminals. It may go towards overfitting also. So that is when we need to use tree pruning. Pruning means, trimming. You can think of a trimming where you are reducing the size of the tree. All right, how to do that? So you first grow the large tree without concerning about overfitting. You just grow. You can prune it back by removing some of the unnecessary or not very important things. But how to find that? So this is again a small technique I'll try to give you. So here we need to perform validation, right? In general machine learning, whenever you do machine learning, there will be training data and testing data, right? So some part of the training data you need to keep for validation, because you treat validation as test data, and once the model is trained, you can apply the validation and find out the error. So you try to minimize that error, not the training error. The goal is always to minimize the validation error, because validation resembles the test data, right? So more specifically, there is cross validation. So these are important but fundamental things. I am assuming here you know what cross validation is, but if not, let me know. I can quickly spend a minute on that. Otherwise, we'll proceed. Yeah. So how do we actually go for finding a best small tree or subtree? We have to estimate the cross validation error for every possible subtree, which is very, very difficult. For example, think of this itself, small tree, right? So whether to split or not at T4, whether to split at T3, whether to split or not at T2. So all these things make decisions based on that. With and without, you have to compute the validation error. What happens if I don't split? What is the error if I don't split? With and without, you have to compute the validation error. What happens if I don't split? What is the error if I don't split at T4? That will be, let us say, some value x1. And what if I split and compute the error? which is minimum. Okay, splitting is giving minimum error, so I'll split. So this is how we should go from the biggest tree to smaller subtree. Wherever if I don't do this split, if it is reducing the minimum validation error, then I'll don't do. If the split is decreasing the validation error, I will retain it. So validation error is very important in pruning and in retaining also. Right. So there is a small algorithm. I'll try to give you the steps. This is also a simple thing only. So what we do is basically, it is called weakest link pruning. Weakest because which increases or which is not really helping us to reduce the cross validation error. So that is what we are removing. So how to find that? So let us say this quantity which I am highlighting, alpha times the cardinality of t. That means the number of terminal nodes. Number of terminal nodes is the number of leaves or number of regions. Essentially, how many regions you are forming, R1, R2, R3, and so on, R5 or R6, how many ever. So if you have more terminals, your cost is increasing. So this will encourage you to reduce your number of terminals, right? So this is an important
Yeah, sir has some technical issue. He will rejoin. Please wait, participants.
All right, I'm back. Is it audible now?
Yes, sir. Yes, sir.
Right. I'm really sorry. There was some network disconnection. Sorry about that. Let me recap. So, all right. So I was trying to, yeah. So I was trying to explain how pruning happens, right? So the first step is grow the large tree using recursive binary splitting, and then apply the cost complexity pruning. So let me show you how we can do. So this is what I've done. So I've started with all the points and then bifurcated into two, and then further this becomes R1 and R2. Then R1 is also split into two. So these are not no more R1. So this becomes R1, this becomes R2, and this becomes R3, right? And so on. I go on doing that until my stopping criterion, which is these terminal regions should have at least 5 points. So that is where I stop. Right now, at the stopping point, I have 7 regions, R1, R2. So my cardinality of T is 7. Now I go to the improved cost, which is finding RSS plus alpha times T, right? I can have a different value of alpha, a positive. Basically, I need to have a positive alpha because I need to encourage minimizing the number of branches or number of terminal regions, right? If I strongly want lesser number, I'll have 100 or 1000. But if I'm okay having more number, I don't need to be this much strict. I can go with 10, 20 things like that. Okay. Again, this is domain dependent. Based on the problem, we should fix these values. All right. So I start from 7. I'll compute the cost, this equation. Let us say it is 123.2. Okay. Now I'll try to reduce one. How? This is the last split, right? Because R6 and R7 are there. So I'll remove this. I'll call only this as R6, right? This is my subtree, one lesser, right? Because I'm removing this split, I'm not performing this split. So I'll compute the cost for this. Let us say cost, remember this is performed on the validation set. While this tree is formed, we completely relied on the training data. But in order to decide on how many number of splits to be used finally, I need to use validation. So I'll use validation data to compute these errors. Let us say this is 116.7. I'm giving some random numbers. Because this is lesser, I'll do similarly. I'll do t is equal to 5, t is equal to 4, and so on. I'll do that. So out of which I'll pick the best one. That is how I'll decide which subtree I should be using finally. So this is pruning. From 7, I went to 6, right? Pruning means, shortening, trimming. So this is how we finally do it, right? So this is the algorithm. Whatever I told you is just into 4 steps actually, right? So this is how it looks also. For example, whatever I've shown you for this problem. So on the x-axis, you have the tree size, right? When it is 2, when it is 4, it is 6, 7, and so on. What is the error? And training error, validation error is in black and green. So we should always go for the cross validation error. Testing, we don't have the test error because testing happens in the end. Once you have fixed your model, that is when testing happens, right? So the cross validation you see with the increase in the tree size, it is reducing, and at this point time, which is 3, number of tree size is 3, it is minimum, and from here it is increasing. The error is increasing, which we don't want. That is why we stop here. So that is why the final model has only 3. Less than 4.5 years is one thing, and less than number of hits is less than 117.5. So this is 1, and this is 2, and this is 3, right? So the other ones which are, we started with 10 actually, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 actually. Yeah, we had 12 regions. We pruned all of them to 3 because that is where the cross validation error is minimum. And rightly so, the test error is also, sorry, here, the test error is also minimum at this point. That is why cross validation is very, very important in machine learning. You need to keep some training data as validation data and choose the hyperparameters based on the validation error, whatever minimizes my validation. All right. So this is about regression trees. So how about classification? Can we use these decision trees for classification? Yes, we can use it. So how do we do? It is very similar to the regression trees, except the predicting variable is a qualitative response. As I told, classification doesn't assign a continuous value. Instead, it will assign only the um, predefined values, right? Set of values, labels only it will assign. So that is what we should also do. Yes. So how to decide? You split everything into the regions, and how to decide what value to be predicted. Whatever is the most commonly occurring label, whatever is the commonly occurring class of the training data in that region, you pick that label and assign to the prediction. That's it. You do everything similar to what we have done. You compute error and try to go minimize the error. And once it is found, how to predict? So earlier we were computing the mean response because the value there is continuous variable. Here, the value is not a continuous variable, it is label. So you take the majority voting. If one particular label has more frequency than the other, then assign that only. So RSS is also not very straightforward here, right? So there RSS makes sense because y minus mean of y squared is continuous variable. Y continuous variable, so error can be continuous value. But here classification problem is little different. How to decide the error? There may be a question. Let me visit that. Okay. All right. So the classification error is the deciding factor whether to is here the residual sum of squares is classification error here. Agreeing with the majority. One class, right? That is ideal situation, but it doesn't happen. Majority of them belong to one class, and there will be some samples that belong to other class. So how to find that? So this is one measure. The fraction of the training observations that do not belong which is 0.1, which is to different class. Let us say only 50% of them belong to one class, and then the half of the samples belong to class 2, class 3, class 4. So in that case, error is more. 1 minus 0.5, it becomes 0.5. 50 further, right? So that is equivalent of RSS. It's a simple metric again. Classification error, 1 minus the majority percentage. There are multiple other ways of doing this cross entropy. For example, Gini index minimizes the total variance. See close numbers to 1 or 0, right? For example, ideally, all the samples in a region belong to one class. In that case, PMK becomes 1. M is the region RM, K is the class. Let us say in the classification problem, you will have K classes. In our example of eye color, which is black, brown, and blue, K is 3, right? So you want to see very strong associations. As long as PMK belongs close to 0 or 1, this value, the cost. So we need to come up with the metric which is equivalent to RSS. So Gini index is one thing, and entropy is also another thing. So P log P. As long as P is close to 1 or 0, this metric is smaller, right? Based on this, you will decide whether to split or not split. All right. Yeah, so any of the three metrics can be used. If the classification accuracy is what is being preferred, generally, because classification accuracy is what is important, right? So that is why any of these metrics can be used. All right, let us take a simple example here also, which is how we can take some medical cholesterol level, other heart and lung function measurements, right? So this is how it looks like. Almium. This is also one of the blood, whether it is in level A or level BC. So this is like it is not a continuous value. It is in less, moderate, or high level. There are three levels for thalmium. One is less, and second is medium, third is high. So high, you will take this branch, right? So again, after that, there is another variable based on which you are bifurcating. And here also, the same variable is used for bifurcating. And also, you go on doing this and come up with a prediction, yes or no, right? So if this condition met, yes, the patient has a heart disease. And the rest of them, yeah, here also there is an S, right? So after that, you need to do the pruning also. You can do the pruning. How? Again, cross-validation. You need to have alpha some positive quantity and then go on finding the validation error, cross-validation error. Wherever the cross-validation is minimum, you have to pick that. So this is the uh, subtree. This is the subset of the nodes which gives the cross-validation minimum. So you have only 1, 2, 3, 4, 5, 6 regions here. Instead of having so many regions, you will have only 6, right? Based on these variables, you will predict yes. The right branch, calcium in the blood, maybe. Yeah. So if it is less than 0.5, you are saying yes. But if it is greater than 0.5 also, you are saying yes. Then why to actually differentiate? You can simply say yes here, right? Purity. Node purity means, for example, here there are 11 training examples. All of them are yes. Let us say these are in the right side. You have only, uh, let us say 7 of 11 are positive, and the rest of the 4 are negative, right? Because the majority is positive, you have to say positive only. But compared to the right side, left side is more confident, right? Because all the training data in this cluster is positive. So 100% confidently you can say if a test sample falls in this region, you're going to have heart disease. But here, if it falls here, you can reduce the confidence. I am only 70% confident that this candidate has uh, heart disease, right? That is the reason why we are bifurcating and assigning the same label. Although the label is same, the confidence with which we are saying is different because of the training data, the purity of the node, right? Sometimes you may also encounter this kind of problems. Not problem, this kind of a behavior. All right, so that is mostly about the trees, but I just want to compare as a last point because these are not the best models, right? Trees, but at the same time, linear regression, linear logistic regression, things like that are also not very sophisticated. Sometimes there will be confusion for the users what to use, which model to use when. Again, there is no clear answer. It depends on the problem. If the relationship between the features and the output is well approximated by a linear model, you should go for linear regression. There was a question in the initial, during the initial slides, whether we can use this for non-linear data. Yes. If there is a highly non-linear and complex relationship, maybe decision trees perform better than the classical methods like linear regression. For example, if this is the space, right? So the green side is one class and yellow side is one class. Clearly the boundary is linear, right? You can go for a linear regression or linear logistic regression. Things will be very, very clear. The model will clearly learn class 1 and class 2. But in this case, if you learn decision trees, this is how it will look like. So this region will be yellow, this region will be green, and again this region will be yellow. But if you see, this will be misclassified, and here this will be misclassified, and this corner will be misclassified, right? When you know that input output relation is linear, go for linear models. If it is non-linear like this, take this corner. So all the yellow is one class, the green is another class. So in this case, linear model will not do well. There will be regions where it misclassifies wrongly, right? So instead, if you go for decision trees, it will be very accurate. Sorry. So in this case, you can split by -1 here and 1 here. Clearly, you can get very close to 100% accuracy. Yes, the problem, yeah, the summary is basically which model is better depends on the problem. If we know that input output relations are close to linear, go for linear. Otherwise, if it is non-linear, go for trees. All right. So I was saying advantage is very simple. Trees are very easy to explain. It can be displayed graphically. Even a non-expert can understand what is happening, and it can handle qualitative variables that are not continuous also, right? The disadvantage is generally they do not have same level of predictive accuracy as the sophisticated models like deep neural networks or any other things. And they can be non-robust also. What do we mean by robust? Non-robust? When there is a small change in the data, for example, some of the points you are adding may add, right? In that case, the changes you need to make in the trees will be more, maybe more. It is not always, but sometimes it may be more. Even if you add small changes in the training data, you may have to do a lot of changes in the tree. So that is one disadvantage. All right, so that's from my side about the trees. So yeah, I may have taken a little longer. Yeah. You can have questions, answers if you have any questions.
Good afternoon, sir.
Good afternoon.
Sir, what is cross validation error method, sir?
I'll tell you. Yes, it's good. So generally what happens is, so when you have, are you able to see the white screen?
Yes, sir. Yes, sir.
So generally what happens is, this is training data and this is, sorry, testing data. I'll show it in a red one. So this is testing data. This will not be there. This is not available. So once your model is given, everything is ready, then you will take to the test error, right? This is not available to you test. So what you do is you take some portion of the training data as validation, right? So you build the model on this green side and test it on the validation data. So whatever change of hyperparameters, for example, in our model, alpha is the hyperparameter. We want to choose, and T is also how many regions we should have. That is a hyperparameter. So in order to find this, we use this portion. Whichever T value that minimizes the error on the validation data, we will pick that one, right? So this is called validation. But what is cross validation? Cross validation means, so which part of the training data to use? We don't know. Somebody picks this data, or I may pick this for validation, or somebody else may pick this for validation. So what we do is we split it equally. Let us say 5 portions, TR1, TR2, and so on, TR5. Okay, so let me write it here. So this is TR1, this is TR2, 3, 4, 5. Let us say this is 3, this is 4, and there is another thing 5. I've made 5 equal splits, right? This is important, so let us spend some time. It's general machine learning, so everybody should understand what is cross validation. So what I'll do is I'll train my model on this 4 and test it on this 5, this guy. So whatever error I get, is called E1. Now, next time what I'll do, I'll train the same model, but this time I'll train on these four. I'll use this for testing. So whatever error I get, I'll get E2, right? So I'm just changing the testing. First I tested on this, training on the four. Next I used the other four and tested on this. Similarly, next time I train on these four and test on this. That will become E3, right? And so on. I'll test finally on this one and train on this one. So every time I'm leaving one of them and rest of them I'm using for training, right? So because I made 5 splits, I'll get 5 errors, E4 and E5, right? So if I make 6 splits, I'll get 6 errors. I'll take the mean of them. So E mean, error mean. So this is called uh, the validation error. Instead of just picking one portion, I'm making equal splits, and every time I'm doing, leaving one out. So this is called leaving one out strategy also, because you never know, based on what you pick, your error may be different. So in order to compensate for that variability, I'll I'll find the mean error on an average. What will be my validation error? How to do that? Just change your validation set every time you pick a different validation and then compute the error. So in the end, you will have a mean error. This is the representative error. It may be same as some of them. It may be different, but on an average, you will know what is the estimated test error. So this is called cross validation because you are changing every time the validation set. Yeah, I hope it is clear.
Yes, sir, understood, sir.
Yeah.
Thank you, sir.
No problem.
Yeah, Kondareddy sir,
Yes.
I believe that no one have any doubts. If any
Okay.
doubts are there, please mail us. We will forward that to sir because
Okay.
it's time to end the session. That's why. Thank you, sir. Thank you for being in our session.
No.
And again, next session also, Kondareddy sir only will be taking the session. If you are having any queries, you can ask in that session also.
Yes. Yes.
Okay.
Yeah.
Yes, sir.
Thank you, ma'am. I'll see you
Yes,
at 2
sir.
o'clock.
Yes, sir. Thank you, sir.
Yeah.
Yeah, dear participants, have 1 hour of lunch break and we will meet at session 3, which is at 12 o'clock. Okay, thank you. And I request all of you to fill the feedback form which was shared in the chat box and also in the WhatsApp group. Please fill that one also. Thank you. Thank you for your cooperation. Yeah, dear participants, recordings all will be shared at the 6th day. Okay. All if any material was shared